Okay, one follow-up to our gravity, right? One follow-up to our acceleration in one dimension. I want to bring up this term of free fall. I think you guys all know what it generally means, right? But there's probably a slight difference from what you're actually used to. When we talk about free fall, you're not actually talking about somebody jumping out of an airplane. Okay, even if they're skydiving, they're not actually in free fall because they have the force of wind working against them. And the longer they fall, the faster they go, the more that the wind actually pushes against them to keep them in the air. So eventually they hit something called terminal velocity, fastest velocity, ending velocity, right? So as things fall, they fall faster and faster and faster, and they get more wind pushing against them because they're going faster. So a good example of that terminal velocity is if you've ever stuck your hand out the window, driving around town, you might feel a slight breeze, right? From the car going through town, going 30 miles an hour, you feel a slight breeze over your hand. But if you try and do that on the highway, the thing's going to bat your hand back because your car is going so much faster. Your hand is inside of the car, so it's going at the same speed. It's going so much faster. And even on a calm day, you're pushing through the wind, so the wind is now pushing against you. Every action has an equal and opposite reaction. We're going to get to that one later. But you put your hand out, and again, just because your hand is going faster, the wind now pushes it like crazy. All right? So on Earth, you tend to never actually see free fall. You only really get free fall in a vacuum, okay? So that means like on the moon, in space, places where you have a vacuum chamber, you can suck all the air out. There's nothing to interfere with the fall, okay? But we can kind of conceptually think about this. Galileo did this too, okay? So he did this by having round objects he dropped from a tower. There were, in fact, forces of air working on the thing, but he got a pretty good result overall. So, one thing to think about, if you're Galileo, let's say you go to the Leaning Tower of Pisa, which I don't believe is actually where he was when he did this, but you got a nice clear shot at the ground now instead of hitting the wall on the way down, okay? So here you are, standing up here, and in one hand you have a hammer, and in the other you have a feather, right? And now you're sucking all the air out, okay? Thankfully, you have a spacesuit on. You are on Leaning Tower of Pisa on the moon, okay? Right? So there's no air to resist you at any point. So now you drop both of these objects off the edge. You drop them at the same height at the same time, okay? And in fact, let's go ahead and do that here. I have to figure out how to do that. There we go. Okay. I have two different objects, and even on Earth, generally speaking, as long as they have enough weight to them, right, which a feather wouldn't, but it still should work in space where there's no air. If I drop two things at the same time, they fall at exactly the same rate. They fall at exactly the same rate. Now, why doesn't a feather do that on Earth? Because, this will be our standard feather, because of air resistance. It had nothing to do with the force of gravity. If it was only gravity alone, there is no air resistance whatsoever. This thing still weighs the same amount. It starts to fall at exactly the same rate now. So, hammer, feather, doesn't matter. Everything falls at the exact same rate, which is gravity. Okay? And again, acceleration due to gravity, at least on Earth, changes where you go by the size of the planet, the mass of the planet, the density of the planet, moreover, more than anything else. Acceleration due to gravity is 10 meters per second squared. So if he drops this hammer and this feather, this is a really awful feather, but you get the idea. Hammer and feather, at any time that you come and look at this thing falling, they're going to be going at exactly the same rate. They're going to fall, and they're both going to hit the ground at exactly the same time. Okay? They hit the ground together if it's in a vacuum. And if it's not, you have that air resistance piece to move things around for you. Okay? So that's all well and good. It's good to know things fall at the same rate. It's a very consistent result. But what I want you guys to think about is that frame of reference business we've been thinking about. Remember, this is your x and this is your y, right? In fact, let's draw it on the board. Started drawing it out wrong. What do you think about that? All right, x, y, right? This is up and down, this is side to side, isn't it? What happens if you're laying down on your side? Does that still give you a case for you? Looks a little bit weirder now, doesn't it? So, what is x and y to you is now different from what is x and y to me, isn't it? Likewise, other things like this can happen, not just how you turn your head or if you stand on your head, right? But maybe if you start falling, right? Or if you start moving in a car. If you start moving in a car, all of a sudden, and this is kind of a weird result, but kind of a thing you've probably had happen to you before. If you are, let's draw a bigger car, a really awesome car, my standard #1 amazing car, okay? Here you are, you wake up in the car, somebody else has been driving, right? There you are, stretched out, relaxed, right? Chilling in the seat, okay? And then all of a sudden, you wake up, and you have this moment where you're just kind of slightly disoriented. After you wake up, you see that there are trees. It looks more like a sketch person's head there. Okay, so you have trees that look like they're actually going really fast backwards, right? And you look like, if you see like an animal on the side of the road, this is going to be a really awesome deer here, right? This is totally a deer, not a dog or a horse, right? Whatever. Okay, this is, judge me if you like. I don't know why I'm drawing the leg there. Apparently it has an udder. Okay, so there we go. Here's the back legs and here's the deer tail. See, now you can tell it's a deer, right? Or a moose or something. Okay. But it's also going to look like this thing is actually traveling backwards at a really fast rate. At the exact same rate as the tree, maybe. Okay? But then you're going to wake up all the way and realize, oh, that's not what's happening. These guys aren't moving, right? What's happening is that, in fact, I am moving, right? My car is moving. But you know what? You weren't wrong to begin with. If you are going at a constant velocity, if v is a constant, you're not having any accelerations, it turns out that you were actually right the first time. You're also right the second time. Both cases are actually a totally valid way of looking at things, okay? So, if you have a constant velocity and it's not changing, you're not experiencing an acceleration, things can look really weird to you. Everything can kind of get flipped around, okay? So if I take, and I stand here on the ground, and here you are, you're going to fall briefly. I'm not going to let this thing fall all the way, right? But briefly, what you see is that, right, you get a really crazy thing happening. All of a sudden, it looks like I'm moving past you upwards, okay? When in fact, you are just standing still. But really, you're falling, okay? So, if you fall, I want you to think about this. If you fall, here you are, standing on the ground. What acceleration do you feel? Well, my feet are on the ground. I'm having to push up against it so I don't slump over sideways, right? I'm pushing down, so therefore the ground is pushing up, and what I actually feel is an acceleration of gravity that's -10 meters per second squared, and that's downwards. That's the thing pushing me into the ground, okay? But what happens when the bottom drops out? Well, you start to fall. You start to gain velocity, don't you? You get an acceleration. Your acceleration is equal to the acceleration of gravity because you're in free fall. But what do you feel? You feel weightless. You feel weightless because you're not having to fight against gravity. So according to you, right, everything around you would have an acceleration upwards potentially. Kind of a weird thing, isn't it? And if somebody dropped a rock or a pen or a marker at the same time that you started falling, it started falling alongside you, it would have the exact same acceleration as you, wouldn't it? So if the rock is falling and you're falling, what do you see? Every time you look over, you see the rock. There it is. Here I am, here's the rock. It's not moving. From my frame of reference, it looks like it's not moving at all because we're accelerating at the same rate. And that's a weird result. Later on when we get into forces, we're going to talk about this. And actually, if you're on an elevator and it starts to move downwards, it starts to accelerate, moreover, and more importantly, it starts to accelerate downwards, all of a sudden you start to feel like you weigh less because guess what? You do. You actually do weigh less because you're pushing against the floor with less force, okay? But the real key thing I want you to get right now when we're talking about acceleration is that if you are R2-D2, I don't know why I have one of these, but my kids have one, right? And you're dropping this pen, and you guys fall, when you're looking at each other, you see, better yet, we got a better example than that, right? I got all these kinds of toys around here for my kids. How about this? Let's get Sharkman and R2-D2 are going to look at each other as they're falling and watch what they do if I'm really careful about how I release them. They're going to be staring each other in the eye all the way down. And if you rewind that, you'll be able to see that a little better. So if you're in free fall, it looks like everything around you is falling as well in the same rate. Well, it's kind of a weird result. Here's another weird result. I need to find a rope of some kind. How about a snake? That'll work, right? Okay. So if you are doing this, right, going around and around, well, if I throw something up into the air, what does it want to do? It wants to make a parabola. It wants to go across like this. The motion of any object, if we're standing on Earth, we fire something up, and Earth, by the way, is totally flat, right? Whatever. Okay, so if we fire anything up at an angle, what you're going to find out is that it always comes back down as a parabola. It's got a little speed in the X, a little speed in the Y, which we're going to get into later on, but it always comes in and hits the ground as a parabola. Velocity's up like this, slows down, right? But then it comes back down a little faster, a little faster, a little faster, right? Now imagine this. And this is what Newton did, by the way. You're not on flat Earth, because we don't exist on a flat Earth. You're on a curved Earth. And you're shooting this thing so fast that now the thing doesn't come back to hit the ground, right? If you don't shoot it fast enough, if you shoot it too fast, it'll kind of arc, and then it'll kind of like continue on into space. If you shoot it too fast, it'll have a trajectory like this, and then it's gone. It's hit escape velocity. It's actually away from the Earth. But if you don't fire it too fast, and you don't fire it too slow, if you fire it too slow, maybe it kind of comes back and hits the Earth over here. But if you fire it at just kind of a sweet spot, and there's a lot of sweet spots in there, okay? Then what this thing is going to do is it's not ever going to hit the Earth. It's going to start traveling like this, right? Maybe it's going to get pulled down. It's going to have a velocity like that. It's going to get pulled towards the Earth. But as it gets accelerated down towards the Earth, it's also moving in this direction. So you end up with a vector like this, and guess what? It ends up falling so that later on its position is over here, and it misses the Earth. And again, it's getting pulled towards the Earth with an acceleration, but it already has a speed like that, so it ends up with a new velocity like this, right? And falls over here, and it misses the Earth again. And what we call that is an orbit. Because now in orbit, it's constantly changing its direction. It's constantly missing the Earth. And so these people, what they're doing is they're constantly falling down towards Earth, but they keep missing it. So they're constantly falling. The reason that you're weightless when you're in space is not because you're far away from gravity. It's because you're in free fall. Just like when you fall down, if you get on a trampoline and go really high, you get that weightless feeling in your stomach as you fall back down. That's what they experience 100% of the time. And when they set a marker out and they let it go, well, it turns out that that marker just stays there floating. Why? Because it's falling at the same rate as they are going around the Earth. And so they see things as floating without moving, unless they're given an initial velocity in terms of the interior of that satellite, or that, not satellite, but the space station, right? So this is kind of a weird thing. When we get to free fall later on, I want you guys to realize that we take away gravity in a sense for that frame of reference. Okay, you no longer feel gravity because you're falling with gravity at the same rate as gravity, so you take it away. If you're on a space station, you don't feel gravity. Weirdly enough, maybe 50 years down the road, they'll have the right materials to actually take, and from Earth, send up a tether, or rather down a tether, from an asteroid. And that asteroid will be traveling around Earth at the same rate that it's rotating. Okay, so they'll actually be able to put a solid thing, or fairly solid thing, between the two, and it'll keep rotating at the same rate that it goes around. They'll stay tethered together. Then you could send an elevator up on that thing, and just use electricity instead of rocket fuel, which is kind of cool. Or you can bring it down from the asteroid, right? So as this thing goes up and away, the farther you get away, and when we talk about gravity forces, it'll make more sense also, you would still have an acceleration due to gravity even way out here. It would be less than it is close to the center of the planet. The closer to the center of the planet you are, the stronger it is. But you would still have an acceleration due to gravity out here. So even though you're the same height away, you'd actually still experience gravity. Why? Because in this sense, you would not be in free fall. You would be going straight up away from the Earth. You wouldn't be falling and missing the Earth. You would just be going straight up and away from the Earth, like climbing a tower. If you get to the top of the Sears Tower, you still feel gravity, and you don't realize it because it's a very small change in height, but you actually experience slightly less gravity there too. They can actually geologists can figure out what's under the Earth. If you have a big blob of something dense over here, right? It has more mass, so it attracts stuff to it more. You can actually figure out changes in the Earth by setting the same device around the Earth. You can actually measure your height away from the Earth if you're on a mountain by setting the same device out there that they call a gravimeter, or a gravity meter, right? You can actually measure the changes in the force of gravity with something like this. It's just a mass on a spring. It's really, really sensitive. So, interesting things, okay? So free fall is when two things are falling together at the same rate as they go, okay? They will fall and see each other fall. You will experience it as weightlessness. all right, or a lack of gravity because of your reference frames. So reference frames totally matter. They totally matter in physics.